begin with this short warm-up where we're evaluating the expressions below. For example, part A, we have 2 to the 0 power. What is 2 to the 0 power? What is anything to the 0 power? It's equal to 1. Okay, we then move on to the next one. 2 to the first. Anything to the first will be itself, right? So 2 to the first will be 2. All right. What about C? Is there a power such that 2 to this power gets me equal to exactly 0? I mean, think about it. If we try 1, it gets us back to 2. If we try 0, it gets us back to 1. If we try something like -1, it would give us a fraction, 1/2. There actually is no number out there that will get us back to a 0. It is not possible. Okay? All right. Now, we know how to do exponents. Do we know how to do logarithms? Maybe, maybe not. We did this last week. Maybe you guys forgot. So let's go over how to do this. Log base 2 of 1. What does this mean? If I were to translate this into an exponential statement, log base 2 of 1 means 2 to the power of what gives you 1? Well, didn't we just answer that above? 2 to the 0 power is equal to 1. So you're basically looking for the exponent. Anytime you evaluate a logarithm, you're looking for an exponent. Log base 2 of 2. 2 to the what power gives you 2? Well, that'll be 1. You want to get back to what you started with. All right. And then lastly, log base 2 of 0. Is there a power that would get us back to 0? Well, we just found in part C that there isn't. So this is also not possible. Okay. All right. Now, this idea of anything to the 0 equals 1 and log base 2 of 2, where like you have the same base basically, like here log base 2 of 2. Anytime you have that case happening where the base and your answer are the same, it's always going to equal 1. And so we're going to use that a little later today when we do transformations. I don't want to get too far ahead of myself, but yeah, this is like a preview of what we're going to see later today. Okay. All right. Anyway, so our first section of guided notes, we want to review how to graph an exponential function. This is something we learned right before winter break. It was unit 4. And we have the equation y equals, there should be an a, although we don't necessarily need it, but it's a times b to the x. And so how do we sketch the graph of an exponential function? Well, there's a few things you guys need to know. One of the first things you need to know is, what is the base? What is the value of b? Because depending on what the value of b is, it's going to change how your graph looks. If it's a value of b greater than 1, it's going to be an increasing function, meaning it goes up. If it's a value of b less than 1, then it's something that's going to go decreasing. So you guys will get a look there. That package over here. Okay, so in this case, we have base 2. Base 2 is greater than 1, so what should this tell us? Is it increasing or decreasing? What do you guys think? Increasing or decreasing? Will it go up or will it go down? Just take a guess. Up. Good. So this is increasing. Okay. What else do we need? Oh, we need to know the following. What is the locator point? We talked about this property. Anything to the 0 is equal to what? 1. Right? Anything to the 0 is equal to 1. Well, guess what? If it's anything to the 0 equal to 1, then it doesn't matter what my base is. It is always going to go to the same point. So my locator point will be the point 0, 1. Okay, and then lastly, what is the horizontal asymptote? Well, the horizontal asymptote for any exponential function is going to be the x-axis. So we will label that y equals 0. Got it? All right, so we haven't really done any math. All we're doing is just kind of like identifying important information from here. And so now we're going to use that information to actually sketch a function. All right, so this is a locator point through 0, 1. So I'll go ahead and put a point there. This is 0, 1. And it's just a sketch, so it doesn't have to be perfect. Next, I want to draw my my horizontal asymptote, which is the x-axis. I'm just going to draw a dashed line down here, and I'm going to label that HA for horizontal asymptote, y equals 0. All right, lastly, we have an increasing function. So it's going to go up. We're going to go from the bottom to the top. Now, when you draw this, you want to start out close to the x-axis, and then as soon as you hit your locator point, you want to start to go up, like immediately up, like this. Okay. All right. So this is what we end up getting as the graph for y equals 2 to the x. It is an increasing function, meaning you start out close to your horizontal asymptote, you hit the locator point, and then you immediately start going up. Okay? All right. So now I want to show you the next one where the base will be a number less than 1, and we'll kind of see how that changes things. All right. Let's move on to the next one. Y equals 1/2 to the x. Here our base is the function, or sorry, the number 1/2, which is less than 1. So this will be a decreasing function. The locator point will remain the same through 0, 1, and our horizontal asymptote will also remain the same through y equals 0. So now that you want to sketch this, we'll begin by doing your horizontal asymptote, just a line through y equals 0, dashed line. Next, make a point through 0, 1. And then you want to go ahead and show the inverse. Instead of going like from the bottom to the top, now we start from the top and we go to the bottom. So we're coming in from the top like this. You hit the locator point, and then you start to hug the x-axis. Now, I do want to make a point here. This is something that I forgot to do in the last example. But you may be wondering, well, how do we know that we're going to go like to the bottom and then to the right? Like, how does that work? Well, you need to figure out, basically, you want to make sure you have at least 2 points on this. And right now we only have 1 point. So I'm kind of like giving that away to you, that this is what it's going to look like. But that's not what it's supposed to look like, unless you know for a fact, because you have those 2 points. So let me show you then, just to confirm our work. So we know that when we have 1/2 to the 0, we get 1. So in this case, that's a point 0, 1. So let's take another point. Let's take another x value. Give me another number, less than 5, because I don't want to make it too big. Let's actually, I'll just give it to you. How about 2? So you're going to give me a big number. I know, sorry. 1/2 squared. What is 1/2 squared? Well, 1/2 squared is 1/2 times 1/2, which is 1/4, right? So in this case, if this were to be a point, the 2 would be the x value, and the 1/4 would be the y value. So it would look like this. 2, 1/4. And so if you were to put that on the graph, it would be to the right of our locator point, which is down here. So it would go through, or our curve would go through this point. So I'll just have to leave it 2, 1/4. Okay. And that second point is there just basically to confirm the direction of our graph, just to like make sure that, yeah, it's gonna continue getting smaller, and it's gonna continue going to the right, basically. All right. So this is like the only, I guess, challenging part, is you do have to make some calculations to find that second point. So let me go back to the first one since I forgot to do this. All right. In this example, we had 2 to the x, so we had the following point, right? We said 2 to the 0 is 1. Well, let me do 2 squared. That's 4. So this would be a point 0, 1, and this would be a point 2 and 4. And so I could make that second point. It would be like over here. And I would just label it 2 and 4. Okay. And so once again, that second point, which you guys can see here, this second point is just confirming that it's going in this direction. That's why we're getting this increasing function. All right. We will explore logarithmic functions in just a bit, and it is very critical that you guys make that second point to receive full credit, or just to basically show the correctness of the graph, right? Like, is it going in that direction? Okay. So before I move on, I just want to make a quick point. Look at the functions. We are going, once again, if it's an increasing function, we're going from the bottom to the top. If it's decreasing, we're coming from the top, going to the bottom. I want you guys to keep these graphs, these functions, the way they look in your mind, because I'm going to show you the inverse, and it is going to look a little differently. But remember, the inverse is the opposite. But there is still some symmetry if you look at those graphs. All right, so now what I want you guys to do is take out your laptops, and you're going to go to student.desmos.com, and you're going to try this code out. This is the only section of Desmos we'll be doing for today. The rest I will be doing up here on the board. Okay, so you're only doing slides 1 through 4. And we'll come back right now. So we have this slide here, slide 2. What I wanted you guys to kind of look at from slide 2 was the following. We have the first graph, b to the x, which is our exponential function, labeled in red. And then we have the logarithmic function, which is the one labeled in blue. And we can see that there is a dashed, like a dotted line right in between them, right? So here's the exponential going up, here is the logarithmic going that way, and then we have a line of symmetry. Now, what I want you guys to remember about this is that because they are inverses, this dashed line in the middle is a line of symmetry. This is where they reflect. This is a mirror effect, right? So this and this are the same. Now, one of the first things that you have here in the slide is, well, you can mess around with the slider. You can make your base either bigger or you can make it smaller. Now, I want you guys to tell me what happens as I make b bigger. What's happening with the functions? Are they getting flatter? Are they going steeper? What's happening there? They're separating, and they are getting steeper. You can tell that they're being steeper because they are kind of flattening. They're getting pulled, kind of like the exponential one's getting pulled left, the other one's getting pulled down, meaning that we are getting to higher numbers quicker. If I make my base less than 1.5, then what happens? Do they intersect? Yes, we can see that they intersect. It actually does happen to be that they not only intersect with each other, but they also go over that dashed line, that line of symmetry. Now, just because there's a line of symmetry doesn't mean that you can't cross it or that it's a limit. This is not an asymptote. This line of symmetry is not an asymptote. This is just a reflection for that mirror effect, which you can continue to see. This and this are mirrored, and then these sections on the inside are also mirrored. And then watch what happens when I make these a number less than 1. Now what's happening with the direction? Did they switch direction, or are they still going in the same direction? Think about if they're increasing or decreasing. Like, if I were to draw the following, because this is the easiest way to tell if something is increasing or decreasing. You use the following. Use the stickman method. You draw a stickman, and then you ask yourself, well, is the stickman going up or down? And it's very simple, very easy to tell. In this case, the stickman is going down for the exponential function, and he is also walking down the slope for the logarithmic function. So it is something that is common between these, and that is that whenever your base is a number less than 1, you are going to flip. You're going to change direction, going from an increasing to now a decreasing function. All right? So I also want to show you guys what happens when I make my base equal to exactly 1? Do we see a curve on the graph anymore? No, we don't see anything. We just see the point 1, 0. Now, the reason why this happens is because this would not be displayed, otherwise it wouldn't be a function. And what I mean by that is, think about the following. If, going back to an exponential function, if with an exponential function, let me show you in the last slide. I think it makes more sense with the last slide. When I make this exactly equal to 1, you will notice that I get a straight line. This right here represents the exponential function. And the reason why we get a straight line is because 1 to the power of anything will always be itself, right? You could multiply 1 times itself as many times as you want, it will always be 1. That's why we get a straight line. But because now we have the inverse, instead of a straight horizontal line, it is displayed as a straight vertical line, but we just can't see it. Because if we saw it, like I said, it wouldn't be considered a function. It wouldn't pass the vertical line test. If we think back to what a function is, a function basically is anytime you have an input to only one output. You cannot have an input that has multiple outputs. All right, that is why in slide 2, or even in this slide, we still have the logarithm still shown technically. You just see the horizontal line. Like I said, you don't see a vertical line because it's not a function. Now, one other thing I want to show you that I find important about this is are the points of intersection. I want you guys to focus on these points of intersection. Okay. For this one, we said, okay, that's the locator point. That's the point 0, 1. For the bottom one, now it's 1, 0. I want you to tell me if these points change as B changes, okay? All right, so I'm going to make B something very large, and I'm going to tap on those numbers again. Are those numbers still there? I still see 0, 1 here, and I still see 1, 0. Let me switch directions now. Let me make something like a fraction. All right, guess what? 0, 1 is still here, and so is 1, 0. The reason why these points don't change is because, going back to that property of exponents, anything to the 0 is 1. The logarithm of anything of 1 is always 0. These are inverse functions, so these points will remain the same no matter what you are looking at. Okay? All right. I think in terms of questions, that pretty much wraps up everything that... oh, just one final thing I would say is notice how we have the asymptote. So for the exponential function in red, our asymptote is the x-axis, meaning we cannot cross the x-axis. We cannot go below 0. Well, now with the other function, we have a vertical asymptote, which is the y-axis. So now we cannot go to the left of the y-axis. That is just something you guys have to consider as we continue working on this. All right? So I think that's kind of all that I want to get out of this from the Desmos. I want to go back now to the notes and have you guys actually start practicing how to graph logarithmic functions from scratch. All right, so let's go back to the notes. I think you guys can put your laptops away for now. We won't be needing them. And I will be showing you how to sketch the graph of y equals log base 2 of x. All right. So just like before, if we go back to the exponential function stuff, what were some of the things that we did here? Let's look back at our steps. Well, the first thing we did was we determined what the value of b was given to us. So if we look at the value of b for y equals log base x, 2 of x, you'll notice that our value of b is 2. Since this is a 2, we can pretty much determine that this will be an increasing function. All right. Next, you have your locator point. So the locator point for an exponential function used to be 0, 1, but because this is the inverse, we flip it. Instead of 0, 1, now we write it backwards. We write it as 1, 0. So your locator point will be the point 1, 0. And then if the asymptote for the exponential function used to be y equals 0, since this is the inverse, we will now switch that to x equals 0. Okay? So that would be our asymptote for this function. Okay? All right. Awesome. Well, we have basically all that we need, except that we are missing our second point. Now, let's think back to this locator point. So I told you guys the following. Log base 2 of 1 is equal to 0. Now, the reason why this works is because 2 to the 0 power is 1. This is something that will be the case for any logarithmic function that you are given. No matter what the base is, when you evaluate log base of 1, your answer will always be 0. Okay, so this gives you the point 0, 1, 0. Sorry. Oh, yeah. It's Jason's song right there. Okay, here is the second point that you need to think about. You are now going to evaluate log base of the base. So it needs to be the same. Log base, in this case base 2, of the base. So log base 2 of 2. That's the second point that you're going to evaluate. Log base 2 of 2. Because anytime you evaluate log base of the base, your answer will be 1. It will be itself. And so this will give you your second point, which for us, it will be the point 2, 1. And obviously, these as x and y coordinates. Okay. So essentially, you need, I guess, what, 5 things? You need to know your base, you need your locator point, your asymptote, and then 2 points, or 1 point, I guess, 1 extra point. So now we can graph this, and we'll begin by just start off with the asymptote. We know that we have an asymptote, vertical asymptote through x equals 0. So it looks something like that. And then we have a locator point through 1, 0. So that'll be here on the x-axis as an x-intercept. And then now that we know our second point, the second point would be 2 and 1. So that would be somewhere over here. And we can label that as 2 and 1. And so all we have to do is just pretty much connect these points. You're going to start off by hugging the asymptote here. And then as soon as you hit your locator point, veer off to the right like that. Okay. And so this gives you the graph. We can tell that it's increasing. If we were to walk this, if we were to like show the stickman this, he would be walking up the slope. It's not a very steep slope, but he'd still be walking it up. Here is your locator point, and here is your additional point. All right. Keep in mind that the locator point here, 1, 0, is shared by all functions, all parent functions, at least for logarithmic functions. And so is the asymptote. Okay, so that's not going to change. All right. Any questions before I move on to the next one? Okay, then let me jump to the next example. So sketch the graph of y equals log base 1/2 of x. So we're going to begin by doing the same process, right? Start by listing the base. What is the base? For this problem, y equals log base 1/2 of x. Log base 1/2 of x. So what is the base? Instead of like 5 times. 1/2. So the base is 1/2. So if it's less than 1, it's decreasing, right? So this will be a decreasing function. What else did we talk about? We said that the locator point will always be 1, 0, and our vertical asymptote will always be x equals 0. Good song, you guys. Good song. Called Summer Madness, in case you're wondering. All right. So let's go back now. We have our base, we have our locator point, we have our asymptote. We just need an additional point. Let's go ahead and find that. You are going to evaluate the following. Log base 1/2 of 1/2. And what will log base 1/2 of 1/2 give you? Log base of the base will always give you 1. So that's your second point, which is the point 1/2, comma 1. Okay. All right. Let's begin. Let's start graphing this. Start with your asymptote. Up and down, up and down. That is the point x, or the line x equals 0. We have a point through 1, comma 0. And then I'm going to zoom in for this one. The second point is the point 1/2, comma 1. That's 1/2, comma 1. So it's right before our locator point. And so if you were to connect these points, or these dots here, you would start off from the top, hugging the asymptote. You would now hit your locator point and veer off to the right like that. And so this would show you that decreasing function, which you get whenever you have a base less than 1. Once again, if you were to draw a stick man over here, he would be walking down the mountain, down the slope like that, right? So this shows decreasing. All right. So I'll leave this up. You guys go ahead and try the next two on your own. All right. What is the base for the first example? What is the base? I will take anyone who raises their hand politely. Kyle, go ahead. Base is 1/4. So is this increasing or decreasing? Decreasing. Good. This is decreasing. What is the vertical asymptote? What is the vertical asymptote? Dylan. X equals 0. What is the locator point? Giovanni. 1, 0. We just need one more thing. The second point. Remember, log base of the base. Log base 1/4 of 1/4 is equal to 1. So your point will be 1/4 over 1. All right. Excellent. We have everything we need. Let's go ahead and graph now. So here is the asymptote. X equals 0. Here is our first point through 1, comma 0. Here is our second point through 1/4 and 1. Connect your points. You cannot go to the left of the asymptote. Okay? So this is the shape that we get, not straight lines, not curves that go down and then up and then the squigglies and this. No, it's just a curve. Like that, like an L almost. Okay? So 4 things. You need to know 4 things. Number 1, the base. Number 2, the vertical asymptote. Number 3, the locator point. Number 4 is a second point, second coordinate, so you can graph it. All right, let's go through one more, and then after that, I think we're going to take our break. Okay. Y equals log base 6 of x. What is the base for this example? 6. So this will be increasing. Locator point is still 1, 0. Vertical asymptote is still x equals 0. Let's find our second point. Second point, log base 6 of 6 is equal to 1. So the point will be 6, comma 1. Okay. Let's go ahead and graph this. Asymptote. X equals 0 is the asymptote. Locator point through 1, 0. Additional point through 6 and 1. Start out by hugging the asymptote. And there you go. Here's your second one. Okay. Once again, it's a curve. start off close to the asymptote, hit the locator point, go through the second point, and show your arrows. All right. It is not that difficult. So we are going to explore transformations when we come back from break, and that's going to add just a slightly bit of a challenge, but should be fine. Let's take 10 minutes. Okay. So yeah, we're reintroducing H and K, and you should know once again the x coordinate for the locator point is H plus 1. Before I go any further, let's just remind ourselves H is responsible for moving in which direction? From what we've seen in the past, where does H move the graph? Left and right, left and right. So K moves up and down. All right. So the locator point for transformed logarithmic functions will be H plus 1 comma K. The vertical asymptote will be the following: x equals H. That's what it will be. Yep. All right. So you guys ready for some examples? Let's do it. Suppose we want to graph the function y equals log base 3 of x plus 1 plus 5. In this case, the steps will be the same. We're just going to add a little bit more. So not only do we want to identify the base value, but now we also want to identify h and k. So let's go ahead and do that right now. So log base 3, so base 3. What is the value of h? X plus 1. So do I write positive 1 as my h value? Or do I change it? Change it to a negative 1. And then k equals 5. All right, locator point is h plus 1 comma k. So if that is the case, then h will be negative 1 plus 1 comma 5, or 0 comma 5. My locator point is 0, 5. Then my vertical asymptote is x equals h, so that would give me x equals negative 1. All right. So we have one point, which is the locator point. Just like we did earlier, we need a second point. So this is where things are going to get a little more challenging. So follow along in this next section. So we know from our work earlier that whenever you take log base of the base, you get 1. So in this case, log base 3 of 3 would give me 1. But there is a little bit of a problem, and that is that our function is not log base 3 of 3, meaning there's like transformation. So I'm going to rewrite the function. The function itself is actually log base 3 of x plus 1 plus 5. Now, we want the stuff on the inside to equal 3. That's what we're looking for. Because we know when we take log base 3 of 3, it'll equal 1. So we want that x plus 1 to become a 3. So what you do is you set those two equal to each other. You're going to set x plus 1 equal to 3 to figure out what x needs to be. Right? The two highlighted things, you set them equal to each other. So if x plus 1 equals 3, what must x equal? 2. That is your coordinate. That is your first coordinate of the second point, is x equals 2. All right. We're going to take this 2, and now we're actually going to plug that back into the original function, log base 3 of x plus 1 plus 5. That'll become log base 3 of 2 plus 1 plus 5. Because now we're looking for the y coordinate. So we're going to solve this out. This will become log base 3 of 3 plus 5. But from our work earlier, anytime you take the log base of the base, you get what? So what does all of this become? Log base 3 of 3 becomes 1. So really, this is 1 plus 5. And what's 1 plus 5? 6. So your second coordinate is 6. So you have an x coordinate of 2 and a y coordinate of 6. That'll be your second point. Second point, 2 comma 6. Okay. So now we have everything we need. Does anyone need this, or can I kind of scroll away? All right. So let's begin then by doing the vertical asymptote first. Straight line through x equals -1. Next, we're going to do our locator point through 0, 5, which would be like up here somewhere. And then our second point will be the point 2 comma 6, which will be like over here. And so we're just going to connect the points now. Which will give us this following shape. Yep. So once again, the asymptote is clearly labeled here. We have our 2 points, and we have our correct curve, right? This is an increasing function, so it's going to look like that. All right. Finish writing this down. I'm going to go over the next one, and that's it for today's lesson in terms of what I'm teaching. I'm going to assign 2 questions to you after that, which I need those to be done before you walk out today. Any extra time that you have left over, I would encourage you to work on your practice. All right, let's finish this lesson then. Let's move on to the last section. Suppose you want to graph log base 1/3 of x minus 3 minus 4. Well, first off, the base is 1/3. Second thing, h is positive 3. Finally, k is -4. So we begin by identifying those 3 things. Given that the locator point is h plus 1 comma k, then that would give me 3 plus 1 comma -4, which will become 4 comma -4. So that's my locator point. 4 comma -4. Finally, since the vertical asymptote is x equals h, then it simply is going to equal x equals 3. That's my vertical asymptote. Okay, we're like 75% done. I'm very sure. We just need to find the second point. All right, pay attention. It's going to go by quick. So we want log base 1/3 of 1/3, since we know that's going to equal 1. Right? Okay. But we don't have log base 1/3 of x. We have log base 1/3 of x x minus 3. So really we have this. Log base 1/3 of x minus 3 minus 4. So we want the stuff on the inside, we want the inputs to be the same. We want x minus 3 to equal 1/3. So we're going to set them equal to each other. Set x minus 3 equal to 1/3. All right, x minus 3 equal to 1/3. This is a one-step equation. This is stuff that you guys did in like 6th grade, 7th grade. How do you get x by itself? Plus 3 on both sides. So we get x equals 3 1/3 or 3.33. So that's your x coordinate. Take this x coordinate, plug it back into the function. Log base 1/3 of, you could write it as 3.33 or 3 1/3 as a mixed number, doesn't matter. I'll do 3.33 minus 3 minus 4. And all of this right here in pink, all of this will become what? Log base 1/3 of 1/3 will become what? 1. All of this will become 1. So really it's just 1 minus 4. So what's 1 minus 4? -3. So your second point is 3.33 and -3. That is your second point. Now we have everything, so we can graph this. First, an asymptote through x equals 3. Next, a point through 4 and -4. Next, a point through 3.33 and 3. (3.33 and -3). Finally, connect your points. And there you have it. All right. Any questions? So, it is 10:07. You guys get out at 10:30. That means you have about 20 minutes, give or take, to get the next page finished. I'm not going to require you guys to finish Desmos, so don't worry about that. Get the next page finished as your exit ticket, and then if you finish that and I check it, then you can work on the practice. Otherwise, this time is yours. Thank you.